Hello, everybody. Welcome to the Ask the Pro series. The Ask the Pro series is powered by the Coffee Technicians program. If you're interested in developing your skills as a coffee technician, you can check out the Coffee Technicians program, an educational program for new and experienced technicians alike, available at the foundation, intermediate, and professional levels. The Coffee Technicians program consists of 6 modules: coffee machines, hydraulics, electrical, water and preventative maintenance, operations management, and coffee preparation. Learn more at sca.coffee/coffeetech. That's sca.coffee/coffeetech. And over to you.
All right. Welcome everyone to Ask the Pro Season 4, Episode 4. Today we are breaking the code and reading electrical schematics with Mr. Michael Tehan. We're going to learn how to read electrical diagrams and schematics for espresso machines. And our panel today, as I said, our speaker is Michael Tehan of Analog Coffee. On the panel, Kurt Benedict could not make it today. We miss him dearly. We have Maria Cleveland from Ernex, me, Keegan from Canteen.
Yeah, I may have missed it. Sorry. Sorry.
Yeah, no worries.
They're here in spirit.
Yeah, Caleb Leach is here in spirit along with Kurt. And moderating today, we have Highland Joseph of Espresso Partners. Get through the introduction here. Important disclaimer, this presentation is for informational purposes only. The views and opinions expressed in this webcast are those of the presenters and do not necessarily reflect the official policy or position of any aspect of the Specialty Coffee Association or the companies the panelists may represent. Welcome to the Ask the Pro series. This is our 4th season, and we are committed to presenting these episodes throughout the year, so please save Fridays at 8 a.m. Pacific Standard Time for the Coffee Tech Guild. All right.
Okay, Maria, good morning. What kind of coffee are you drinking?
You know what? I am in Orange County today, and I've got a cup of El Salvador from Martin Dietrich's team at Keegans Coffee.
Oh, really? How is it?
It's delicious. I was able to visit them right when they opened at 6, got a little walk in Huntington Beach, and now here we're webinaring. So today's a good day.
Mike, what are you having for coffee?
I'm a creature of habit. I've got my dark Ethiopian Yirgacheffe, doing an Americano today because I'm still on that diet.
How's that diet going for you?
7 pounds the first week. So
that's actually good.
Yeah, so I'm sticking to it. I'm not cheating.
Keegan, how about you?
Well, I am mixing 2 coffees today because it's the end of a bag. So I have some Rwanda from Dollop and then a dark blend from Passion House. And it actually mixed up pretty well, so not too disappointed here.
Yeah, I have the same thing. I just don't know what it is, but it's actually tasty. It's made off of a Cuisinart coffee machine, which I somehow procured. Good morning, everybody. Welcome to Ask the Pro. Today we're going to do schematics with Michael Tehan. He's going to talk to us about how to read electrical diagrams and schematics for espresso machines. We're going to discuss some troubleshooting theory and kind of learn how to use that map to troubleshoot and fix the machine. So let's go dark, everybody. Mike, I'm going to turn it over to you. And
okay.
Viewers, if you have any questions, feel free and post them, and I will ask Mike as we go. Thanks, you guys.
Sounds good. Okay. Oh, that's right. I did the slide too. Sorry. In terms of basic, what every tech needs to know, even just to get started. You can't start from absolute nothing. You have to have a basic understanding of how, what the difference between low voltage is and line voltage. Basic electrical safety, so you don't kill yourself your first day on the job. One thing that's really good to know are terms that are in both Italian and English. A lot of manufacturers now are putting actual English words on the diagrams and on the boxes, which is helpful, but not always the case. So we kind of go over some of that a little bit today too. Basic wiring, like how thick of a wire you should use, how connectors work, how to even check connectors. You know, a lot of the basic stuff, but mostly we're trying to focus on how to actually look at diagrams and understand the wiring of them. And the last thing, of course, is common sense. Don't do any of this kind of stuff with power onto the machine unless you are really, really good at knowing what you're doing. It is a dangerous, dangerous thing. You know, people used to say that 220 is actually safer than 110 because it knocks you on your ass. But either way, electricity can kill you, so be careful. Let's move on.
Hey, Mike, I got a question for you.
Yeah.
This is one of the things that we discuss in the content group a lot. How important is a meter, an electrical meter, knowing the ins and outs of an electrical meter when you're working on diagrams and schematics?
When looking at diagrams, when you're just looking at diagrams, it's not that important.
Okay.
But when you're actually applying what you're looking at to the machine, don't even open a machine without a meter.
Okay.
Yeah, it's pointless, absolutely pointless.
Okay, back to you, my
Okay.
man.
All right, so what I want to kind of cover is that there's two kinds of diagrams you're going to read. There's a diagram that's going to be in some of the manuals of the machines, whether it's a repair manual, sometimes they're actually in owner's manuals. And those kinds of diagrams are very detailed. I'm kind of surprised why the detail on this one didn't come through. And it covers everything in the machine, the power coming in, all the flow meters, basically where all the wires go. You're not always going to have access to that whenever you're on the job site, though. But invariably, there will be a diagram on the box. And the diagram on the box just covers basic fundamentals. It's like the top level you know, overview of what is connected to the machine and how things are connected. And they read differently. So what I kind of want to cover both, because in some aspects, if you're doing a deep dive of a machine, there's a connection you can't track down. The schematics are going to be valuable. But for a lot of the stuff, when you're just trying to figure out why something isn't working, or how they're running, you know, a connection to a flow meter, or, you know, where's the common leg, you can find a lot of that information actually on the box. So we're going to cover both today. So let's go. Okay, the first thing I wanted to cover, actually, before getting to the schematics, and only because I get this a lot, well, I used to get it a lot, has to do with how the machine is actually wired. There's a difference that all the machines that are coming out of Italy, for example, Italy or Spain, even France, the wiring is very, very consistent. You're not going to get 16 different kinds of wiring coming out of there. If you look at the left-hand side, though, this is what it would look like on the schematic, where you've got a power cord coming in. And generally these days, a lot of power cords are basically 3-wire cords. You have a ground leg, you have a neutral leg, and you have a hot leg. Whether it's 110 or 220, anything coming out of the European community is going to have a hot, a neutral, and a ground. The US treats that differently on 220 machines. The machine functions the same way, but it's kind of important to understand what their mindset is about wiring, to kind of when you're looking at the schematic, though. So I wanted to cover this real quickly because this is the first thing that you do when you get a machine. On all 110 volt machines that come in with a conventional plug, you have a hot leg that goes to the little connector. Usually it's a brass connector. The ground wires on European machines are always color coded with green and yellow. It's got a yellow stripe. The idea is if you're colorblind, you can still identify what the hell it is. I think it's brilliant. I don't know why we don't do it here. For 110 machines and for all 220 machines in Europe, the blue line is typically what's called a neutral. And the neutral doesn't actually carry current to the machine, but it will carry current back from the machine. It's like, you know, for electricity to work, you have to have 2 wires together. The neutral is that other wire. And that blue wire is common to everything in the machine. Now, the difference on the 220 machines here, we're showing an L630 plug. It's the same thing. We've got a hot leg, which is line 1. You've got the ground leg. But in the US, when these machines come over, because we do electricity a little bit differently, that blue neutral line is actually a hot line. So the brown line has 110 volts and the blue line has 110 volts reference to ground, both out of phase. So when they're connected together, the way that you do a hot leg and neutral, you will get 208 or 240, depending how the transformer is wired to the machine, or to the pole. The third one is when you have a 4-wire hookup, because in Europe, sometimes they'll run actually 2 hot phases to the machine usually specifically for the heating element, and they do this because the wiring doesn't have to be quite so big. In the US, we don't have two-phase machines. Everything is essentially a two-phase machine, but we don't actually use neutral in the US on any 220-volt espresso machines. So when you've got that 4-wire cord, you'll have a blue leg, which is one of the hot legs. You'll have a ground, and then you'll have a brown and a black wire. And because we don't split the phases for 220 machines here in the US, you actually put those two wires together and bind them to the same terminal in the cord. And that's how you get around that. So if you look at the diagram on the left-hand side, you'll see some kind of ghost wires. Those are like optional wires. So this machine would have normally come from Europe, for example, with a 3-wire cord, and that black and blue wire, that red and blue wire would be hooked up. If you had a 4 or even a 5-wire cord, they would go to additional terminals on the main switch. A lot of companies will actually go ahead and wire them separately. They won't jumper them like it showed here. So you would do that jumpering in the cord cap as it connects to the wall. So that's the basics. Let's move on.
Quick question, Michael.
Yeah.
When you're wiring a 110-volt plug, if someone were to switch the live and the neutral, what is the impact of that?
Okay, the machine itself doesn't know the difference. Okay, because you're working with AC current, the machine will operate normally. The downside, the problem is that because Europe assumes that neutral wire doesn't carry current when you're manufacturing the machine, that wire is connected to every component in the machine and not switched after the switch. So when it's on, if you switch them in the plug, that common wire that's feeding the machine, that wire is actually hot. So if you're doing testing or probing around or something like that, with nothing running, you wouldn't expect to get shocked anywhere. But if you switch it in the plug, you have a live 110-volt line connecting everything in the machine. So don't do that.
Thank you.
Okay. Okay, terms and translations. One of the things that came up a long time ago with technicians in particular is American techs, their Italian usually isn't very good. I don't speak Italian, but I can understand Italian when people are speaking it around me a little bit. I did a diagram like this for a catalog I put together, 15 years ago. And it talks about what the terms mean on the box. And this might be something that maybe we can even print out or make available, because it's like a Rosetta Stone for an electronic box. So I'm just going to very quickly go over a lot of the basic terms. When you look at a box, you'll see terms like phase or alimentary or element, and that's basically the power coming in. The phase is always the hot leg. That's always assumed to be the hot leg. Common, COM, is what in Europe would come over as the neutral wire. And common is very key here, because that common leg is the common leg that's going everywhere. And a lot of times on some of the larger boxes, what they'll do is, instead of running that common wire directly from the switch and bypassing the box, they'll actually run all the power to the box and then jumper it in the box and then take it back out of the box. But keep in mind that common wire on a 220 machine in the US is hot. It's a hot leg. So don't assume that you're not going to get shocked if you're playing around in that machine if the power's on. EV1, EV2, those are considered electrovalves. It's basically short for electrovalve. Sometimes we'll call them solenoid valves here, but in Europe, it's basically just called an electrovalve. A boiler is called a caldaya. A caldaya is basically it's a boiler. And usually what that refers to is the inlet solenoid valve. And so whenever you see something on the box, that's what that means. Sonda simply means sensor. Now there's a few different kinds of sensors you're going to see. So like a sonda sicurezza, a lot of machines will have 2 probes. On home machines, you'll have a probe in the boiler, and you might have 2 probes in the boiler and an additional one in the reservoir in the back. Sonda sicurezza, basically it's the safety probe. If you have a machine that's got 2 probes, generally what it will do is it'll delay heating or turning on the heating elements for the machine until that lower level probe is satisfied, and that's the sonda sicurezza. Sonda livello just is kind of what it sounds like. It's the sensor for the level control. I'm getting ahead of myself. The sonda sicurezza serbataio, which, excuse me for my bad pronunciation of Italian, by the way, I'm sorry, it's early. That's typically what you would find in a reservoir. This box here is a very, very basic box. The other fun thing is sometimes you'll see the abbreviation for SM and S with a lower M. Those are both level controls as well, depending on how much room they have on the box to write things. The uppercase M is the main probe, and the lowercase probe, or lowercase m, is the longer security probe. That's the one that just senses like the baseline level of water in the boiler. Alimentari, same thing as phase. But generally, what alimentari does is that refers to the general voltage of the machine. You won't always see that on the incoming wires. Resistenza, heating element. A heating element is a resistant. It's a resistor. It's basically a big fat resistor, because whenever you have resistance in line with electricity, it creates heat. So basically, they're just kind of going back to fundamentals. The heating element is a resistor. Massa is ground. Sometimes what you'll see on boxes is there will be a connection on the box to massa. Basically, it's designed to ground the probe, and that ensures that you have to have that ground wire in some way connected to the boiler of the machine so it can complete the circuit for the level. Pumpa, pump, and sicurezza. Let's see, reading my old stuff here. Sometimes you'll have an output for on the sicurezza side on some boxes, especially the ones that won't turn on the heating element until you have a minimum level of water in the boiler. And the sicurezza without sonda attached to it is generally the output for the relay that turns on the heating element. And sometimes it'll also be called the heating element. So any questions on my budget translation so far?
A good translation. Like, two things for our viewers: we provide copies of the decks for all of our presentations. At the end of this episode, we will put an email that you can reach out to me and get a copy of it, or if you're on Slack, feel free and reach out to our team on Slack, and we're happy to send you a copy, and we'll post it. Mike, if you look at the bottom, there's a series of numbers: 02, 03, 04. What does that mean?
I think those are date codes.
Okay.
Yeah, I don't think that I've never. Not all boxes have them, and I simply think they're date codes because they're marked at the same time that they're actually marking the outside of the box for voltage.
Okay.
Okay. Other fun stuff about boards. Boards are generally broken down into two sectors, and they keep them divided. And the reason they do that is so they can kind of keep the high voltage side separate from the low voltage side. So and this is true like almost any box these days. On the hot side, that's all the power coming in, main power, all the power that's coming into the box and all the power that's coming out of the box. So we'll start with the hot side first. If you look at the hot side, you see the main power coming in, and you'll actually see there's a hot leg that comes in that goes into the box, and then it's internally jumpered to all the components and all the relays that are coming off of the board. And that's the switched leg. That's the one that the box actually has control over. So when solenoids come on, relays come on, whatever's happening out of the box, that's the leg that the box uses through the relays that are inside the board to send power to the machine to perform whatever function that you want. The other leg, if you look at it where it comes in on the left-hand side, the common leg, that's actually also jumpered inside the box. And that actually, it comes right back out of that jumper and connects to the other side of all the components in the machine. So if you look inside a machine, sometimes you'll see that common blue wire that connects every component in the machine. It'll connect all the solenoid valves. It'll connect, motors. Everything in the machine will have this blue wire that's connected to it. That blue wire is not actually switched or controlled in any way by that box. The box simply redistributes it from there. Sometimes it'll come out of the switch, but a lot of times it'll just kind of come out of the box. And the reason for that too is that when you disconnect terminals from the box, you're essentially disconnecting everything from the machine. So if you take a connector off the hot side of a box like this, then you have, even if the switch is on, you won't have power going to any of the components on the machine. It puts the box in the middle of everything, even though one of those legs isn't switched at all. You'll see a lot of the same terms here. Pump, fill. GR1 refers to a group solenoid. This particular box has an output for steam and an output for the heating element. Now, what's important to note too, a lot of these boards will have all of these connections, but you won't have wires going to all of them. So basically, when they manufacture a board, they're manufacturing a template with different processors on them that can be applied to a number of different machines. So, for example, this board here would control, an automatic steam switch. It would have an automatic water switch if you don't have a regular water valve. Some of them will output to LCDs and things like this that machine might not even use. So there's a lot of stuff that might be on a board that don't even apply to the machine that you've got. Now on the low voltage side is basically everything typically 12 volts or 24 volts and under. If you have like low voltage solenoids, for example, that might be coming out of this side of the board. But generally speaking, you're talking about keyboards, ribbon cables, flow meters, because flow meters are all low voltage, level probes, level sensors. So basically, to get that low voltage, everything passes through a transformer on the board. So on one side, you've got high voltage, on the other side, you've got low voltage. So any questions so far? At least you know what side of the board it won't kill you.
Exactly. To our viewers, if you have questions per slide, please feel free and ask when we'll get answered with Mike. You're welcome to ask questions starting now. Our next slide, Mike.
Yep.
You go.
Okay. Let's see if I can zoom in on this one a little bit. Okay, so this is a relatively generic wiring diagram. There's nothing, I had to pick one. And I'm sure that many manufacturers will do it a little bit differently. This one, though, has color on it. Most of the schematics you're going to see don't have color anywhere. So you're going to be, putting on your glasses and, tracking down the same black line that seems to go everywhere. But on this particular diagram, you can kind of see that one common blue wire that goes everywhere. And if you look at this diagram, the red wire in this case is the hot leg. Now the hot leg is, one wire coming into the machine, and then it's broken down into 3 wires coming off of the main switch through a terminal connector. And basically what it's doing is it's dedicating 2 of those wires, or one, depending on the machine, 1 of those wires directly to the heating element. Because in the machine, you've got the electronic controls that come from the main switch, and then you have the heating system, which is controlled separately. So except for some of the modern machines where PID controllers and temperature controllers are actually on the main board, and pressure controllers. Hang on one second, guys. I'm going to move to another room. Guys. Snowball, go. Sorry about the delay here. I have dogs that have to get sequestered. Because our cleaning crew is here early. Go. Okay. And with that, we're back. Sorry about that. Okay. Oh gosh, where was I? Okay. Let's see. Okay, so in terms of components on the machine, here we'll cover some of the basics. So what I was saying, getting back to where I was, again, I'm getting a little old. So within the system, the machine is basically divided between everything controlling the heating system and everything controlling the electronics, and they're typically separated out. And that's one of the reasons why you have main power switches that have 3 positions. Off, on with electronics, so that you can actually test the machine and see how things are working. before you actually apply power to the heating elements, make sure the boiler's full, all those kinds of things. And then that second switch, that number 2 position on the switch is what actually engages the heating elements. And that's why the machine's kind of separated out that way. So if you have an issue with a heating element not getting hot, it's probably nothing to do with the main board. It's got something to do with that main current that's actually coming from the switch to the element or the element itself. So in terms of what things look like, the main switch, one of the things you'll see is like you'll see these like little internal jumpers when the power comes to it. Generally it's labeled or there's some kind of diagram for it, but the main switch will generally have 2 legs. Main switches will actually disengage all the power and the neutral to the machine. It won't just leave the neutral connected. So the main switch, if you're dealing with a 220 volt machine, when you kill the power to the main switch, the machine itself should be dead, should have nothing. Okay. One important thing about this common wire, when you're diagnosing something, because that wire is common, if nothing works on the machine, even though the power is on, look to the common wire, like some kind of break in the common wire, as the fault, because that connects everything. If you only have one component that isn't working, then you can trace it back from the hot leg on coming back from whatever that component is back to the board, because that's the one that's isolated and all by itself. Contactors and main switch look very similar, but you'll see that little additional box in the bottom hand corner in the bottom of that contactor switch. That's actually the relay and the contactor that engages it. Pressure and safety switches are generally dedicated to right before the heating element. Most pressure switches are 3-leg switches to accommodate 3-phase machines. Most machines don't use them all. The ones that do will generally simply kind of piggyback wires, and the reason they do that is to increase the life expectancy of the pressure stat, so less currents going through each leg. Heating elements are always squiggly lines. That the heating element, you went too fast, go back one. On the element side, those squiggly lines are that's the electrical designation on any schematic for a resistor. And hence, heating elements are resistors. That's what they always look like. Probes, they actually kind of look like probes. It's kind of it's not rocket science. They'll usually have it connected in some way to what looks like a boiler, just for a visual representation. On this one, you'll actually see there's a low level and a high level probe. The low level probe, the longer probe, is always the security probe. That's like the baseline, the lowest level of water that will allow you to operate the machine. The upper probe is the standard fill level probe. Okay, now we can move on. Okay, solenoids always look like they've got a box and a cross through them. They're generally always labeled. In some cases, it'll say EV1, EV2, EV3. Sometimes it'll say GR1, GR2, GR3. Sometimes the description might be a little bit better than that. But here on this particular diagram, it's easy to see that common leg, because every component has to have 2 wires that go to it. And that common leg, that blue leg here that's going throughout the entire machine, is connected to all the solenoids and all the relays all the time. And that's the one that's not switched. It comes from the box, but it's not switched. And the solenoid itself is actually controlled by the box itself. And on this particular machine, they actually have high voltage and low voltage components on the machine. And on this particular schematic, the low voltage products items coming out of the box are actually in gray. So high voltage stuff is hot, is red and blue. But on this particular machine, they're using low voltage designations in gray, and that all comes out of the box. In terms of flow meters will generally have 3 wires. And if they don't have 3 wires, that 3rd wire is grounded somewhere to the flow meter itself. And the 3 wires, basically, it's called a Hall's effect sensor. Flow meters require power to operate because it has to create a kind of like a magnetic field. And what it's counting is every time that flow meter reel passes the sensor, it creates a pulse, and that pulse is from electricity generated by the box and then sent back to the box to determine, what the volume of water is coming out of it. It's always going to be low voltage. A lot of times they'll have little lights on them. From a diagnostic standpoint, you can kind of see when they're working, when they flicker at you. Orientation is important for a flow meter. The good thing about flow meters is they're usually attached to a cap, and that cap kind of forces you to put everything in the right orientation anyway. Not all machines have lamps that come out of boxes, but that's what that's what lamps will look like, and they'll generally always be labeled. Probably the most important thing in any machine are ground connections. And you'll see on this schematic, which is true of almost any machine, there are ground connections everywhere. Every individual component that has any power going to it all, that's line voltage, has to be grounded. Because for example, if you have a solenoid valve that shorts out internally, you don't want it to just be a live short. It has to ground somewhere in order to trip that breaker. So you'll see those little ground connectors everywhere. Whenever you've been open up a machine, you'll see ground wires connected to everything. The machine I have here at the house, even the panels that come off the side of the machine have ground wires connected to the panels. The idea is if you remove something from the machine and have it in your hand, that there will always be a ground that's actually connected to that thing that's in your hand. So when it shorts, it doesn't ground to you, it actually grounds to that wire that goes back to the machine. So you'll see ground connections everywhere. Do not fail to reconnect a ground. Now, the one exception is on low voltage components, 24 volt, typically 50 volts or less, but on espresso machines, 24 volts or less. Because 24 volts isn't enough to do any damage to you, and generally the amperage is very low, a ground wire is not required for low voltage components, but it is required for everything else. Okay, we can move on. Am I going too fast this time?
No, you're good. I suspect there's going to be a lot of questions. I got a bunch of questions too, so keep going. You're good. You're doing fine. Okay,
good. A junction strip. Now, one of the things to see about a junction strip is the way you can identify it is it has little screws on top of it. A lot of schematics are actually, they look like what they are. And even, in this case, even the junction strip is grounded, because if something happens on that junction strip, you want to make sure that it's covered. The ground strip isn't so much to protect, you as an operator, as in the event of a failure where any of those hot leads actually touches ground or makes contact with ground, it's designed to blow the circuit breaker, because it's just like an overload of current. And that's why the grounds are important. Pump motor is pretty basic, and that's what a connector looks like. This machine has a couple of things on it that probably don't make it to the US, though. In the US, we don't really care about cup heaters. But this machine, has a cup heater in the bottom right-hand corner. You'll see what that looks like. That's probably the only time that you won't see that little squiggly arm or squiggly line for the resistor, because it's kind of that's what the element kind of looks like, and I think that's just to aid the technician when they're looking at it to kind of see how everything goes. Let's see, anything else about this schematic that looks interesting? No, I think that's it. Any questions?
I have a question.
Yeah.
I see the wire going to the group 2 solenoid is pink. Is there a reason why that one is color coded differently from the other hot legs?
Let's see. Well, if I were to guess, I think they made a mistake on the diagram.
All right. And then one other question. I've come on 110 volt machines before that were installed probably by less experienced technicians, where the ground and neutral were jumped together either at the terminal block or somewhere else.
Uh-huh.
Yeah.
Yeah.
What is the risk there?
Well, okay, the ground wire is never supposed to have current going through it. It's never supposed to have anything going back. So for example, if you were to hook that up to a GFI circuit on 110, because the neutral is always carrying current back, the GFI will sense that current and trip the breaker. Because the ground is like sacrosanct. It's supposed to be just static, nothing. It doesn't get to play with anything. The only exception in the U.S. is on old dryer outlets in older construction, where they would actually have the ground and the neutral together. Back in the circuit breaker panel, they're actually connected. You can connect it there, but you can't connect it anywhere after there because that whole ground circuit has to be like untouched and pristine. You can't mess around with that. And the same thing happens, like for example, if you switch a ground and a neutral in a plug, technically the machine will kind of work, but you're using your lifeline, you're using your safety feature of the electrical system of the house and the way it's designed to actually do work in the machine and not perform its function as a safety feature. And the other thing is, that ground wire is connected to everything in your house or everything in your business. So you don't want to mess with that. I installed a machine once, this is 30 years ago. We were leaking a little bit of voltage to ground. We weren't sure where it was coming from, and I was relatively new in the business. The machine worked fine. Everything was great. It's just that when somebody would run water in the sink, it was about 9 feet from the machine. They would get shocked every time that they put their hand under the water. And we traced it back to the machine because it was leaking voltage to ground, but not enough to trip a breaker, just enough to make things interesting. So yeah, don't switch those. It will perform a lot of the same functions, and it will in fact work, but it would be bad. I've come across a couple of machines where a machine was originally one voltage and then switched to another, like 110, and they didn't have a 110 in the outlet that they were using. So they simply ran that leg directly to ground. It kind of worked, but it's the kind of thing where you can't be using a safety feature as a functional part of the machine. It's there as a safety feature for a reason. So, any other questions? I should see what's on the next slide.
Next slide is.
Or are we done?
We're done.
We are done.
Yeah. Leaking current to ground. You want to explain that concept to some of our newer tech viewers?
Okay, so sometimes, if you have a heating element that's corroded, for example, you've got 110 or 220 volts going to a heating element, and you've got some corrosion around that element. That element will actually that corrosion will sometimes act like a resistor and leak a little bit of voltage to the ground of the machine. It's typically under a lot of resistance, so you're not going to leak a lot of voltage, not enough to actually shock you, and certainly not enough to trip the circuit breaker. But in some cases, you'll get some of that leakage there. The other thing that will happen is if you have a heating element that explodes or melts in an espresso machine and then gets refilled with water, you have the coil of the heating element is actually working, kind of. You'll see this in cases where a machine will get warm but never really get hot. And what's happening is the voltage that's actually feeding the heating element is heating up the water through, it's actually forming a circuit between the water and the boiler of the machine. So instead of doing its normal path in the heating element, which might be 22 or 25 ohms, depending on the machine, that's creating heat, it's actually energizing the water directly in the machine and using the ground of the machine to complete the circuit. But water resistance is like 600 or 650 ohms, depending on dissolved solids and stuff like that. So basically, you'll have a very low wattage. It'll act like a low wattage heating element. So you're leaking voltage to ground in that case explicitly. You're leaking 110 volts or 220 volts to ground. And the ground wire is completing the circuit, or the ground is completing the circuit through the water in the machine.
Okay, thanks, Mike. Cameras on for our panelists. And we have a question. Mark Roby, one of our content group members, says, minus attending a CTG class, is there a good resource out there for newer tech to review, perhaps from a manufacturer of meters or by an electrical group such as NEMA? I actually can answer part of that question. The basic fluke training, and this is where I will violate the manufacturer rule because they're big supporters, is great. I'm not sure if any of you guys have done it, and it's free. Mike, what do you got?
God, all my resources are with you guys. All of my stuff has been on the job training for the last 30 years. So I don't think that I have any external sources. I think that you guys are a much better outlet or a much better resource than what I have. You know, don't buy the cheapest meter you can find. That's a good start.
Okay, Keegan, you have you're a trainer, you have any additions to that?
I've got a question with regards to meters. You say don't buy the cheapest one you can find. Can you speak to the different functionalities of micro ohms or different things that we should be looking for on a multimeter?
Yeah, do you got that, Highland, or do you want me to?
No, Mike, it's you.
Okay, so most decent meters are multimeters, and they won't always have different designations for the breakdown voltage. Like some of the older meters that had different ranges, you know, it's like from 0 to 50 or 0 to 200 or 0 to 500 or whatever they are. Most multimeters now are, you set it for AC or DC voltage, and then it just auto ranges automatically. Ohms are the same way. Ohms will break down into tenths of an ohm, for example. But for the most part, for what we're looking for in espresso machines, we're looking in somewhere in that range of 0 to 1,000 ohms. We typically don't get higher than that. From 0 to 50 ohms, you're looking at heating elements. That's where you're measuring whether a heating element is sound. Most heating elements are going to be between 8 and 30 ohms, depending on the voltage and the power required. The other reason why you would use an ohm meter for like on solenoid valves, you want to measure the resistance on a coil. A coil might be about 1,200 ohms to see if it's any good. And if you're checking the resistance of water, you can kind of use it as a fake TDS meter. Water is going to come around 600 ohms. The only fun thing is that when you're looking at a meter, you've got the high voltage side, which is kind of basic, but on the low voltage side, some machines will run 24 volts AC to solenoid valves. Sometimes they'll run DC. So how you tell the difference is if you look at the solenoid in your hand, the AC valves will actually have a sine wave attached to the power rating of the machine of the actual valve. Anything DC current, even if it doesn't say, sometimes it'll say CC, but if it doesn't say CC or DC, you'll see a straight line and then a dotted line underneath it. And whenever you see those two lines, that's a DC component. So when you have your meter in your hand, you do have to delineate between AC and DC, because if you're trying to measure DC current with an AC meter, it's not going to read, and vice versa, because just the way the electricity works is fundamentally different.
So I have a controversial question, and this is one that you, me, and Don have gotten into several times, is the importance of having a meter with an amp clamp.
Well, I don't own one. I thought about it, but I don't own one. It's handy if you know how to use it. It's like you can only put it around one wire. You can't put it around two. It's not universal, because I think that that physics still works and electronics still work. If you can measure the resistance of a heating element, then it must match the amperage. In other words, volts, amps, resistance are all tied together. So the nice thing about having an amp meter is you can see what the draw is on a particular leg going to a heating element without actually having to pull it apart and test the resistance. It's kind of a shortcut, but I don't think that you need to have one so long as you you know how to test resistance in a machine. So for example, if you're testing resistance on a heating element, you do have to kind of isolate the heating element. If you don't isolate the heating element, you might be thinking that you're getting resistance on the element, but you're actually getting resistance to the lamp, for example, the heating element lamp on the machine. So it can kind of fake you into something. And the more things that you pile onto resistance in parallel, the lower the resistance is. If it's in series, the higher the resistance. So you just have to isolate them. So amp clamps are convenient, but I'm on the, I don't think you need one, Camp.
Panelist questions?
It must work.
Panelists? Keegan?
Yeah. So are there any clues on a schematic that a technician can use to find out what the expected resistance or voltage at a component of a machine might be? So we have the schematic, we know where everything's flowing, we have an issue and we want to kind of test. Is there anything on that roadmap that'll kind of help us get there?
It'll give you an indication of where to test. It won't necessarily give you an indication of what to test. So for example, it won't tell you what the resistance is going to be at the heating element or what it should be, because the schematics are relatively generic, and they make them for they might make 6 or 10 different versions of that particular machine depending on the market. So the resistance on the heating element might not, they wouldn't be able to put it down specifically. The resistance, basically, if you're under 30 ohms on a resistor leg, it's good. It's just good. Whether it's supposed to be 12, but you're getting 14, it doesn't matter. If you're under 30, it's going to get hot. It's the element. It's not like a precision piece of equipment. It's just a resistor that gets warm. On the schematic side, though, so for example, if you're working with a 220 volt machine and you have a solenoid that's not working, and you can actually check the common leg on that solenoid all the way back to the cord. If the machine, you can unplug it, you can turn the power switch to the machine on, and you can put a probe on what is supposed to be the common leg of that prong on the plug, and you should be able to get continuity to every common wire on that machine, everywhere. So if you've got a solenoid that isn't working, that's dead, for example, and you've tapped it and banged it and done all the other tech tricks you can do to make it come back to life, when you're checking voltage, you'll get current to ground when it's asking for water, when it's supposed to work. But you should also, on a 220 volt machine, get current to ground from that common leg all the time. So if you're not getting current to ground on the common leg, you have a break somewhere in the common. So you can kind of basically, in terms of tracing it down, it's like a maze anyway. So start where you don't have power and keep going back until you do, or start where you have power and go forward until you don't. And that's kind of where you're going to find it. The common leg is not generally in parallel, so it'll go from one component to another, to another, to another, to another in series, and loop all back to itself, and it'll be kind of connected that way. So it's possible that you can have a bad connection in a common leg and then lose the common everywhere after that. So if you have multiple components that are down, then you might have a common wire issue. If you only have one component that's not working, then you can trace that back to the box and that one component that's actually being switched by the box. So the other thing is, if you're dealing with a heating element, the heating element isn't going to run through a box on most machines. So a heating element issue, if you're trying to diagnose that, you don't even have to have the box as being a component part of that, unless there's a security feature in the box. So basically, the schematic kind of tells you like where things are connected and where to look, but it's not going to give you raw data on it.
Mike, I have a question, and actually, Keegan, as a trainer, I have a question to you also. What's the best way, and we'll start with Mike, to train a tech on how to read a schematic? What are some good ideas?
Get a good pair of glasses because they're small.
We're all blind.
Yeah, yeah, and be patient. Fundamentals are always important to me. Whenever I would do training, the first hour of a training is just fundamentals. This is how electricity works. This is what you're going to expect. This is where the high voltage is. This is where the low voltage is. This is where you're going to find a common wire, and this is why the common wire is important. This is why this is why machines that come from Europe into the U.S. look a little bit different than a regular brewer. They don't run neutral lines the way we run neutral lines here, for example. So before you even look at the schematic, for me, it's about fundamental understanding of how electricity flows and how it works. Once you have that basic down, the schematics are pretty straightforward. That the wiring is, it's not going to try to duplicate what the loom looks like inside the machine. Sometimes the loom will split and go different directions. But the schematic is basically, it's kind of like reading a map. That's what we need. We need Google schematics for machines. That's what we need. But no, I think a basic understanding before you look at it is really all that's really important.
Okay, Mark Roby again. Actually, I want to hear Keegan's answer before we go to Mark. Keegan, what about you?
Yeah, so I mean, definitely starting with the basics, difference between AC and DC, Ohm's law, all of that stuff. But when it comes time to actually look at a schematic, what I really like to do is get the schematic out and lay it down next to the machine, bring out the multimeter, and just kind of walk through and show, generally with continuity, okay, look, these two components connect here, let's meter it, and we can prove that connection right there. And even if the wire goes into the loom and disappears and runs through the frame, you can illustrate really cleanly point A to point B to point C, all the way through. And kind of translating that schematic into the physical machine in that way is one way that I found a lot of success to kind of make that abstract drawing make sense in the real world.
Thank you. Okay, now on to Mark Roby's question. I have techs. I have techs more recently that are seeing more coffee brewers 220 volt moving from 4-wire L1, L2, and G to 3-wire L1, L2, G, and they initially get confused on why neutral is no longer needed. Good question, Mark.
It's because they got smart, I think. What brewers did for a long time is that they would have one component that was common to all their machines, whether they were 110 or 220. And rather than have a 220 version of a component or a transformer or something like that, they made everything 110. And so they simply required that you have a 4-wire hookup with a neutral. And which to me seemed kind of pointless, but it was more of a cost-cutting method than anything else. So now, when you eliminate the neutral isn't really necessary if you design the machine around it, because a lot of the components that are now on coffee brewers and espresso machines are low voltage anyway. So you're basically taking whatever the voltage is coming in, and then using low voltage to control all the components inside the machine, whether it's solid state relays or whatever it happens to be. And once you make everything 24 volts, or whatever that voltage happens to be for control, you no longer need the neutral wire, because you can actually use 220 transformers or multi-voltage transformers and run everything either way. I mean, we have, I think the razor that I charge, my rechargeable razor has a plug that you can plug into 110 or 220. It doesn't care. It figures it out. So I would imagine that a lot of the components inside the coffee brewers are doing the same thing. if you have an espresso machine with 3 wires, and the outlet you're plugging it into is a 4-wire outlet, ground, line 1, line 2, and a neutral, you don't use that neutral. You can actually use that as you can actually plug that espresso machine into a 4-wire plug. You're going to connect the ground. You're going to connect the blue wire to one of the hot legs, and then you're going to connect the brown or the brown and black wire to the other hot leg, and you will leave the neutral wire disconnected. It won't even be hooked up, and you can actually use it in a 4-wire plug in that case, because espresso machines in the U.S. don't use neutral the same way.
Okay, and we have a follow-up from Mr. Roby. If you want, why should you not tie ground and neutral together, which techs see all the time in the field? Which is actually going to be my question. Good question, Roby.
Oh, God. Anyone that ties a neutral and a ground together should be terminated.
But I've seen techs do it too. Why is that?
Because they think it doesn't make any difference. Maybe they've got a bad ground somewhere. Maybe they've got a loose, maybe there's a loose wire, in the outlet on the neutral side. They're not getting a good neutral, so they think, oh, I'll just connect it to ground because I know that's always going to work. I mean, fundamentally it works, but it's like it's tantamount to when you get in the, it's like connecting a seat belt in your car before you get in the seat. You're bypassing the fundamental security safety device of the machine. Yes, it will send current through the neutral wire, in the case of a fault. It'll do all kinds of crazy, feedback stuff because you're actually like in a lot of cases in commercial environments, you'll have an outlet is actually connected to a metal conduit. That metal conduit goes all the way back to the box. If you connect a neutral wire to the ground inside the machine, you're actually feeding back voltage through that neutral wire and the ground, which is the conduit that's going back to the box all at the same time. So neutral and ground always have to be isolated because the ground is what keeps you from dying or melting the machine down. So it's just funny. It will work because they're tied back in the box, but every electrical code requirement on the planet says you have to keep them separate. So when you combine them in the machine, you are short-circuiting, not in this euphemistically, the safety function of the electrical code that governs the building. And it's even conceivable that if there's ever a fault that can be traced back to that, call up your insurance company.
Okay, closing statements. Let's start with Keegan. Keegan, you have anything to offer before we wrap it up?
Yeah, I just kind of wanted to answer my own question from earlier about how do we know what expected resistance at a component might be. If you have 2 of that same component and one's working and one's not, test the one that's working and use that as your reference value for the one that's not.
Really good point. Thanks, Keegan. That's a really good point. Maria, would you closing statements? And since you are the lead of next episode, why don't you tell us about next week's episode?
Oh, thank you. So thank you so much. I learned a lot with all the how to trace things back, and also thank you for the tip on learning how to use the multimeter. I think that could be a fun episode in the future. So next week we are going to be talking about the science of cleaning coffee equipment and the science behind the difference of milk cleaners, espresso machine cleaners, things of that nature, and different types of soils that go into some very complex equipment that we have in the market these days.
Excellent. I'm looking forward to that. That was actually one of my favorite episodes of season 2 also. We have one last question from, I'm going to mess this name up, Ionis Fakaris. I'm sorry, Ionis, if I mess it up. When we try to install a machine at a ship's bar where there is no ground, do we have to connect neutral wire with ground? Which we just kind of covered, but let's see if we can answer the question for the gentleman.
I don't know. I have not installed machines in ships. I know a lot of equipment that goes into ships are typically 380 volts. You know, there's got to be some that's something that you have to work out with the ship. Like there's got to be an electrical engineer with the ship, because every machine has a ground, and you have to kind of figure out how they're doing it. I know you're kind of grounding to the vessel of the machine. There might be different. I think that this one's a little bit out of my wheelhouse. Almost any tech in Florida can probably tell you, because I think they all work on cruise ships. I know the voltage is wonky, but I really don't know. I don't think it's ever safe to connect a ground and neutral in a machine. All of that has to happen in the box.
Yeah, Highland, I'm recommending that we have our friend hit us up on Slack, because I know there's many members of our community who, Michael, great idea about our friends down in Florida.
So we're going to wrap it up. Michael, last statements from you.
I hope this made sense to everyone. I enjoy doing these little conversations and sit downs. I hope they're of value.
Thank you. So for anybody who has any questions or comments, you can email me directly. Email was on the board, or you can reach out to us on Slack, where our team will get to you and get you copies of the presentation. Maria, I'm looking forward to next week. Oh, by the way, we had another worldwide audience. And we, again, thank you, Nation of Greece coffee technicians, for attending. We have, like, apparently they're our big fan base. Everybody have a great weekend, and we will see you next week.
All right. Take care. Bye. Bye-bye.
Bye-bye. Thanks.
Thanks, everyone.